Look at a traditional internal combustion engine. It is a dense cluster of moving metal parts, valves, and pistons. When you strip away the body of a modern electric vehicle, that mechanical complexity is replaced by a perfectly flat, dense battery chassis. While the engine bay is now empty, the floor pan contains an integrated electrical architecture that manages power delivery in microseconds. Placing the primary power source directly into the floor pan dictates entirely new parameters for how the vehicle handles, accelerates, and absorbs impact. It also introduces severe, unextinguishable hazards for technicians who treat this architecture like a conventional car. The traditional mechanical drivetrain has been replaced by 4 primary components, known as the Big Four. These 4 electrical nodes operate in extreme symbiosis. If a single component fails, the entire vehicle is immobilized. Together, they form what engineers call the skateboard platform, a self-contained foundation where all power and propulsion sit below the driver's feet. To safely maintain these vehicles and prevent catastrophic workshop fires, professionals have to discard their legacy mechanical habits and learn the strict logic of the high-voltage ecosystem. To understand that ecosystem, we start at the lowest physical point of the vehicle, the floor pan. This animated wireframe isolates the main battery pack. Zooming in, we see it consists of hundreds, sometimes thousands, of individual cylindrical lithium-ion cells. Together, these cells output an immense amount of energy, utilizing a tight operating range of 400 to 800 volts. The pack is bolted directly into the frame, functioning as the primary load-bearing structural spine of the chassis. Layered directly on top of these volatile physical cells is a digital brain, known as the Battery Management System, or BMS. The BMS constantly tracks the individual voltage, thermal spikes, and load balancing of every single cell in real time. Lithium-ion chemistry is highly reactive. Without the BMS intervening to regulate that energy, the pack becomes dangerously unstable. If a temperature spike occurs, the BMS detects it instantly and physically isolates the failing cell, shutting it down before the heat can spread to its neighbors. The battery pack serves a dual purpose. It provides the physical rigidity holding the car together, while acting as the digital baseline keeping the system from destroying itself. The battery pack stores energy as direct current, but the propulsion motor requires 3-phase alternating current to spin. That conversion happens here, inside the power inverter. It receives the DC power and precisely chops it into an AC wave. By adjusting the frequency of that wave, the inverter dictates the exact torque and speed of the motor in real time. This provides the electric vehicle with its signature zero-lag throttle response. Supporting this high-voltage exchange are 2 secondary nodes, the onboard charger and the DC-DC converter. The onboard charger takes alternating current from a standard residential wall plug and converts it back into direct current to recharge the main battery. In this graphic, we see the function of the DC-DC converter. It takes a massive 400-volt block of energy from the main pack and filters it down into a 12-volt output. This reduction is required because the electronic control units, the radio, and the interior lighting still run on a 12-volt architecture. This creates a critical diagnostic trap for technicians. The low-voltage computer network is the only system with the authority to engage the high-voltage contactors. If that 12-volt battery dies, the computer stays offline. It physically cannot command the massive 400-volt system to turn on. A technician ignoring the mundane 12-volt system will be left baffled by an electric vehicle that is fully charged, yet completely immobilized. A combustion drivetrain requires a sprawling footprint of gearboxes, heavy drive shafts, and axles to transfer power to the wheels. Electric mechanics are highly consolidated. This animated diagram explodes the single metallic casing of the electric drive unit, or EDU. Every stage of physical propulsion is housed within these 3 internal parts. First is the electric motor, which receives the AC power from the inverter and generates raw RPM. Next is the reduction gear. Electric motors spin far too fast to drive the wheels directly. The reduction gear steps down that rotational speed to multiply the motor's torque. Finally, we reach the differential. The differential takes that newly multiplied torque and efficiently divides it between the left and right wheel hubs. By housing the motor, gearing, and power distribution in one sealed enclosure, The EDU achieves high mechanical efficiency by consolidating 3 combustion systems into one frictionless unit. Looking at this technical blueprint of an EV suspended on a standard mechanics lift, we see a hidden hazard of this architecture, a significant weight penalty. A standard electric vehicle easily reaches 2.5 tons. Technicians must strictly verify that their hoist load ratings can handle this concentrated mass before lifting. Once in the air, any EV entering a shop mandates a rigorous visual underbody inspection. Inspectors trace the routing of thick orange high-voltage cable, checking for any sagging or friction that could wear through insulation and cause a dangerous short. They also inspect the integrity of the coolant lines. Liquid cooling is vital. A leak here means the battery and inverter will rapidly overheat under heavy load. One of the most dangerous technician errors happens when attempting to lift the vehicle by placing a floor jack directly onto the flat battery casing. This animated cross-section shows the mechanical sequence of that mistake. The physical pressure from the jack dents the casing upward, breaching the thin wrapper of a battery cell and sparking an internal short circuit. That electrical arc instantly spikes the surrounding temperature, forcing the adjacent cells to overheat and fail in a rapid, cascading chain reaction. This is thermal runaway. It is a self-sustaining chemical fire that creates its own oxygen, making it immune to conventional suppression methods. Because the battery serves as the structural floor, minor procedural sloppiness with a jack directly guarantees a systemic, unextinguishable destruction of the vehicle. Now we see the fully assembled skateboard platform, loaded with all 4 high-voltage components, gliding across the test track. The layout creates a distinct dynamic advantage by placing the weight of the structural battery pack at the lowest physical point of the vehicle. This drives the center of gravity straight down to the asphalt, far lower than any top-heavy internal combustion engine. As a result, the vehicle experiences unmatched cornering stability and a near-zero rollover risk during extreme maneuvers. Beyond performance, this architecture demonstrates a massive manufacturing advantage: platform modularity. By keeping the powertrain flat, automakers can drop a sedan, a truck, or an SUV body onto the exact same base platform. Standardizing the high-voltage ecosystem drastically reduces production costs and accelerates assembly line output. From the precise chopping of AC power to the rigid integration of the battery floor pan, the electric vehicle is built purely for maximum efficiency. Navigating the future of automotive engineering requires absolute technical precision. In the high-voltage ecosystem, failing to understand what lies beneath the floorboard carries terminal consequences.